So indeed, I'm Nick. I'm from KU Leuven in Belgium, work as a postdoc student. In this presentation, I will talk about a parallel in time multiple shooting algorithm that uses large eddy simulations, flow reconstruction in the atmospheric boundary layer. So that's quite a mouthful. Let's start with some context and motivation. First of all, the ABL, or the atmospheric boundary layer. So the ABL is actually the lowest part of the atmosphere. Flow is really influenced by whatever is going on at the surface. Think about buildings, forests, wind turbines, whatever. Now, understanding this flow and to be able to modeling it is very important for a whole range of applications, one of which is turbulent flow reconstruction, and that's what I'll talk about today. So with turbulent flow reconstruction, the goal is to reconstruct the turbulent flow field based on whatever measurements we have. And this again is very important for a whole range of other applications. Think about weather forecasting, numerical weather prediction, but also think about control applications. And that's a bit my background. So I'm in the wind farm control community. And of course, if you need to do wind farm control, first you need state estimation, and that basically means reconstructing the turbulent flow in the wind farm. So that's also an application of this turbulent flow reconstruction problem.
Can I just ask a question about the picture? Is this really a picture below?
Yes, this is actually a picture where there was some low-hanging fog that was traveling through the wind farm, and then you can really see the wakes. So this is
But they should not be in the wake of the other ones, right?
Seems bad placement.
Not
indeed, but there's only so much you can do, right, depending on
because
the
the
direction.
direction obviously.
So typically what you do is you try to steer the wakes away
Yeah.
downstream turbines. But I think this is not the conference to talk about that. Yeah, anyway.
Said about that picture.
So as I said, we need to model this, but to model the flow in the ABL, we need control models that can capture these highly complex physics. These physics are usually modeled using the Stokes equations. Some people talked about it yet. In our research group, we are using large eddy simulations as a CFD tool to solve these equations on a computer. That's what we do. Doesn't matter too much what this LES or these large eddy simulations entail, but for the remainder of this presentation, we're just solving a coupled nonlinear PDE. That is particularly large scale due to these large eddy simulations. So take that into account. Now, if you solve this, you can get these nice movies that you can see on top. So that was actually a three-dimensional simulation. I'm only showing a 2D snapshot here, but now you can really see the turbulent fluctuations and so on. So this is the type of flows that we are interested in. Now, these large eddy simulations, as I said, they're very slow, they're very large scale. And because of that, we were trying to use parallel in time methods to speed up these simulations, especially when doing optimization with them. This resulted in a publication now about 2 years ago, where we actually developed a multiple shooting algorithm specifically targeted for large-scale optimal control problems governed by the three-dimensional Navier-Stokes equations. If you're interested in that, I've included the QR code, so please have a look. Now, since then, we have been further improving, further developing this algorithm, and by now we're actually able, for the first time, to the best of our knowledge, to apply it in the context of the three-dimensional Navier-Stokes equations in the turbulent regime. So really the type of flows that I'm showing on the top of the slide here. So that's actually quite nice, and that's also what I will talk about today. So I will further explore the potential of this multiple shooting algorithm for this application, specifically in the context of turbulent flow reconstruction. And then I will also look into more realistic reconstruction scenarios, which are, of course, more interesting from a practical point of view. Now, for this presentation, you will not see fancy tables, fancy speed-up plots, parallel efficiencies, and so on. Those are all included in the publication, so if you're interested, have a look there. Here, I will really talk about applying the multiple shooting algorithm for this application and the issues that we may encounter when doing so. So let's dive into it. So first of all, the methodology. I will first explain what such a turbulent flow reconstruction problem is, and then in the future slides, I will also explain how we can use multiple shooting to solve it. So there's not a lot of explaining that I need to do. So turbulent flow reconstruction, in essence, is a velocity tracking problem that has been introduced before. So basically, what we are doing is we are minimizing the difference between our flow field U and any kind of measurements of this flow field over some time horizon t. The flow, of course, is governed by our large eddy simulations that I included in one of the previous slides. And what we're optimizing for is actually the initial condition. So we're looking for the initial condition that, given the model of our flow, minimizes reconstruction error over the time horizon. This term here is a background term because depending on the measurements, you need some extra regularization to get it working properly. For the remainder of this presentation, it's not that important, so I will not talk too much about that. Now, because we're dealing with the Navier-Stokes equations, this initial condition that we're optimizing also has to be divergence-free. And that actually complicates the formulation a bit. So the way we deal with it is actually as follows. So actually transform this optimization problem into a solenoidal or divergence-free subspace where we then solve the problem. This is done using projection, reconstruction, but this doesn't really matter for the remainder of the presentation. What does matter is, in the end, this optimization problem that we end up with. This is a classical PDE constraint optimization problem that was introduced before as well, where we are now optimizing for phi 0, which denotes the transformed initial condition that minimizes our reconstruction error over the time horizon. So that's the type of PDE constraint problems that we are interested in. So yeah, PDE constraint optimization, it's very large scale because of these large-eddy simulations. So the way people used to solve it is using matrix-free algorithms. So what we did in our research group so far was using limited memory BFGS, and the gradients were computed using a discrete adjoint method, which has also been introduced before. So the way it worked in practice is, I have some animations, so I have to click through them. So we have the initial condition, and then, as explained before, you always start with a forward simulation. So in our case, that's solving these large-eddy simulations. Then you backpropagate, you do the adjoint simulation, you get the gradient, you update your control. So in our case, these initial conditions, and you go again, forward solve, adjoint solve, until you find the trajectory that minimizes the reconstruction error. So that's the way it goes. But what I've been explaining so far is really this single shooting framework where we evaluate from start to finish, which is of course sequential. And this has really become a bottleneck since these large-eddy simulations are so slow. So that's why now we are looking into parallel in time methods to speed up this optimization process. In particular, what we are looking into are multiple shooting methods. So here the idea is basically to subdivide your time horizon into several windows. And now the idea is actually to minimize our reconstruction error in each of these windows. And you also see this in our objective function. Now it's just the sum of the reconstruction errors in each of the windows. However, we also introduced a new set of controls, these phi i's, and they basically denote the initial conditions of the shooting windows. So that's what we have here. Now, in the end, of course, with our multiple shooting method, we want to get the same solution as single shooting. So that basically means that we want a continuous trajectory from start to finish. Whereas here, this is not the case. We have these matching errors. So what we do in our optimization is we include this extra constraint. This is what we call the matching condition. And this basically states that the phi I, so initial condition of one window, should be equal to the terminal condition of the previous window. Because if that's the case, you can find a continuous trajectory and you can basically get the same solution as single shooting. So that's the idea behind it. It has been explained before as well, I guess. But of course, needless to say, the main advantage here is the possibility to do all the simulations in the windows parallel in time. So then the question is, how can we solve it? Well, para-opt has also been explained before, so thank you for that. But yeah, there, of course, the basic idea is, well, do some kind of Newton iteration on the KKT system, and then you use a coarse grid solve, so basically the para-real ID, to compute the Jacobians. So that's one way to do it. So that's also a shooting method. That's not what we do. So in our case, in our multiple shooting method, we are really solving the equality constraint problem as it is using a matrix-free augmented Lagrangian algorithm. And that's what I will talk about in the next few slides. So with this augmented Lagrangian, basically what you do is you transform the equality constraint problem into a sequence of unconstrained problems. And in each unconstrained problem, you minimize the augmented Lagrangian function. I've included it on the slide. This augmented Lagrangian basically consists of three contributions. So you have the objective function, that's the same thing that we have here. Then in green, you have a Lagrangian term, and then in red, you have the penalty term that basically penalizes these matching conditions. So the way it goes is you minimize your subproblem, and then after solving the subproblem, you will update the Lagrangian multipliers here. You will increase the penalty parameter, so to put more weight on minimizing these matching conditions, and you start a new subproblem until you have achieved convergence. So that's the basic idea. And again, of course, this is straightforward to parallelize in time because we have these windows. Now, I have been explaining this augmented Lagrangian approach in a few other conferences, and I don't always have the feeling that people really understand what I mean. So again, I have some animations here. So as I said, in each subproblem, you minimize this augmented Lagrangian. You always start with an initial guess of your control. So in our case, an initial guess of where the shooting windows should start. Then you perform the forward simulations, so the large-eddy simulations, parallel time. Then there is some parallel communication over the windows. So basically communicating the matching error in our case. And based on that, you can start the adjoint simulation, which is also parallel in time over the windows. If you have done the adjoint simulation, you can compute the gradients and you can basically start a gradient-based optimization loop. So in our case, we are using limited memory EFGS. So that's solving the subproblem. After solving the subproblem, solution may look like this. So you can see that we are closer to our reference trajectory, so that's good. But in green, there is still the matching error. So typically what you do is you will update the penalty parameter, you increase it to put more weight on minimizing this matching error. You also update the Lagrangian multipliers and you start a new subproblem until you have achieved conversions. So that's the basic idea. So the main message here is that we will optimize our matching error and our reconstruction error at the same time, which of course has an important implication, namely that we have infeasible trajectories throughout our optimization because of these matching errors. That's important to take into account here. All right, then the important question at this point is, well, when do we have achieved convergence? So basically, when do we have to stop our algorithm? Basic answer here is when our matching error is small enough. And then, of course, the real question is what is small enough? And it turns out that this is actually quite an important question. And the only way to properly answer it is by doing a sequential evaluation over the whole time horizon. I'm going to try to explain why this is very important. So again, we may end up with this solution after solving some subproblem, and we are wondering, okay, maybe this is already good enough. Okay, there is some matching error, but we are reasonably close to our trajectory. Maybe this is just good enough as a solution. So then what I propose is to do a sequential evaluation, and then it's very much possible that you end up in this situation. So doing the simulation over the whole time interval, you actually deviate from your reference trajectory quite a lot. And this is what we often observe in practice. So what happens is that the optimizer really tends to exploit these matching errors to artificially decrease your multiple shooting objective function, which is of course not what we want. The only way to properly assess this effect is by doing the full simulation. Of course, the downside is doing the full simulation over the whole time horizon. It's sequential by nature, so we break the time parallelism here. So that's why we propose to do it only every now and then in practice after solving such a sub-problem. But it's really important to make sure that we don't end up in this situation that I'm showing on the slide. So that's the basic idea here. That's the message that I want to give. Just to put things in perspective, so in our research group, we have been working with this algorithm for a while now. It started 4 years back with Liang, who basically came up with this augmented Lagrangian or started applying it for multiple shooting. Then there was my paper where we applied it in three-dimensional Navier-Stokes and where we looked into time parallelism and so on. And then now what I'm doing now is applying it really into relevant problems, namely the turbulent flow reconstruction problem in LES, and also looking into more realistic scenarios. So those are the main contributions from the last year, I would say. All right. Case setup and results. So let's start applying this algorithm now. So as I said, we are applying it to turbulent flow reconstruction. So the first step here is to perform some kind of a reference simulation. In our case, this is a very fine grid large-eddy simulation. And then we take virtual measurements from this simulation and try to use these measurements to reconstruct the flow. That's the basic idea. However, remark that we use or that we do the reconstruction on a coarser grid resolution because otherwise the thing would be way too expensive. So take that into account for the future slides. We then looked into different scenarios. So first of all, there is case A and case B, where we actually assume that as a measurement, we have the full field available. So that means as a measurement, we really consider full field three-dimensional flow field measurement. So that's what we consider here. And then in particular for case A, we are looking into a situation where there is model mismatch, so making it a bit more realistic. And for case B, we added noise to our measurements to basically see how multiple shooting performs in that situation. So those are case A and case B, full field observations. Then there is also a LiDAR case, which is really more realistic, where we only consider partial observations of our flow originating from LiDAR measurements, which is the way measurements are usually collected in this context. And then, yeah, for each of these scenarios, we have applied our multiple shooting algorithm to see how well it performs, or if it even performs at all. So let's start with that. Case A, as I said, we are considering full field observations of flow, and there is model mismatch in the sense that we take the reference measurements from fine grid LES as we do the reconstruction on a coarser grid. So here we have the results. So left is objective function, right is matching error versus the number of PDE evaluations. Black dotted line is single shooting, so that's the baseline, so to speak. The colored lines are the multiple shooting runs, and then each dot here basically corresponds to one outer iteration of the augmented Lagrangian method. So good news, multiple shooting is working, so you can see that we achieve the same level of convergence as single shooting, so that's good. Matching error is also small enough based on this sequential cost evaluation that we did. We achieve roughly a continuous trajectory, so that's also good. We also looked into the algorithmic speedups. We achieved algorithmic speedups in the order of 1 or 1.3 for a higher number of windows, which is very good. Remember, it is only the algorithmic speedup, so an algorithmic speedup of 1 is actually good enough, given that there is still the parallel in time speedup. I didn't include them here, but for example, for the 50 window case, depending on your parallel efficiency, you can still get a speed up of 40, 45 if you have a very good parallel speed up. So that's really the main advantage of doing this. So multiple shooting is really performing well in this case. Yeah, just to give you some intuition on what results look like. So on the left-hand side, we have a snapshot from the reference flow field. The middle is the reconstruction, and the right-hand side is the reconstruction error. As you can see, we capture the main turbulent dynamics. So qualitatively speaking, it looks very nice. But of course, it's a bit more smeared out because of the fact that we're doing the reconstruction on a coarser grid. But yeah, it looks quite nice. However, this is very interesting because with multiple shooting, we made it an equality constraint optimization problem. We added these additional controls, whereas we still end up with an algorithmic speedup in the order of 1. So multiple shooting is really performing well in this case. And this actually has to do with the way we initialize our shooting windows. What I've been showing before was this picture, and here I basically initialize my shooting windows somewhat randomly. This will not work in practice. So we looked into that in the paper, it will not work. Or it will work, it will converge, but the algorithmic speedups will be very low. However, for this first case, this case A, we have these full field observations. So that basically means that we have our reference trajectory. So we might as well use that to initialize our shooting window, which is also the way we did it in practice. So if you do that, you're already a lot closer to your trajectory. You're really warm starting your method. And this is what results in the nice algorithmic speedups from the previous slide. So the main message here is think about the initialization. It really matters in the performance of the multiple shooting. So that's what I want to say here. Then there is a second case, case B. In the interest of time, I won't explain too much about it. It's just that we added measurements errors to see how multiple shooting performs in that case. Turns out it all worked well. So again, very nice. But again, I won't explain too much. What I do want to talk about, though, is the LiDAR case. So as I said, a LiDAR is the way these measurements are usually collected in practice. And the way that's done is, well, a LiDAR is basically a laser that moves in some kind of a plane and then collects velocity measurements along this LiDAR beam. So the main difference with the previous cases is really that we only have partial observations of our flow. This means that we don't have a full field measurement, so we don't have a straightforward way to initialize our shooting windows. Whereas it turned out that was quite important in the previous slides. So the question is, how does multiple shooting hold up? So here we have the results. Again, in terms of accuracy, multiple shooting roughly reaches the same accuracy as single shooting, so that's good. However, algorithmic speedups are significantly lower. So for example, for the 10 window case, we only have an algorithmic speedup or slowdown of 0.16, which is significantly lower than the previous cases. And this really has to do with this initialization of the shooting windows. To give the full picture, I think for this case, the 10 window case, if we included the parallel and time speedup, still got an overall speedup of, I think, 40%. So that was okay, but we were really hoping for more. So that's really what we're working on, trying to further improve these algorithmic speedups. This is what the results look like. So again, left is reference, right is a reconstruction. Of course, we can only reconstruct so much given that we only have the partial observations. But within the LiDAR plane, again, the reconstruction looks quite nice. We are capturing the main turbulent dynamics. So from a practical point of view, this is actually quite nice given that we were able to do this using multiple shooting. So to repeat myself again, why it didn't work is because we don't have the proper initialization of the shooting windows. But there's more. So with this LiDAR case, it turned out that it was very difficult within our augmented Lagrangian framework to find the proper trade-off between either minimizing your actual reconstruction error or minimizing this matching error. So it turned out that our optimizer was always exploiting the matching error to get the reconstruction error down, and yeah, it was more difficult to get it working in this case. So there's also some future work that we'll have ahead of us. And that brings me to the end of the presentation. So some conclusions. I think I presented the parallel and time multiple shooting algorithm for the three-dimensional Navier-Stokes equations in the turbulent regime. Seemed to work. I think I've shown the potential of the approach, especially for the full field cases. That was really working quite nicely. But there is some future work to be done to also get the algorithmic speedups up for the more realistic cases like this LiDAR case. In particular, we noticed that tuning our augmented Lagrangian is quite cumbersome. So now we are looking into more automated parameter tuning methods, but also just other optimization methods as a whole. So there was this paper by Liang, who developed a sequential quadratic programming framework for this application. And there it actually seemed to outperform the augmented Lagrangian for more simplistic cases. So maybe this is the way forward. It's something that we're still looking into now. And in the long run, we also want to apply it to non-tracking cases, but that's really significantly more. I think that brings me to the end of the presentation. Thanks for listening. I'm open to questions.